Hello everyone, and welcome to the OneClass channel. Good evening, my name is Fejiro, and I am an Honors Bachelor of Science student graduate working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college levels. Just to make sure that you can hear me, double checking. Perfect. So today we'll be going over, as I said, some chemistry questions at both the high school and college levels. If you need some homework or help tutoring, make sure you click on the link down below. And now with that, let's hop straight into our lesson for today, starting with question 1. So we should be seeing it here. And the first question is just to draw the Lewis structure for CH5N. So let's begin, shall we? So question 1, drawing that Lewis structure. So the way we do this question, first we want to just list out the atoms we have. We have a carbon, we have 5 hydrogens, and we have a nitrogen. So the way these Lewis structures usually work is that we want to organize it in a way where everything is fulfilled, but we find that out actually. So we definitely need help from our trusty periodic table. So right there we have it ready. And so we have carbon, and carbon has 4 valence electrons, so we're just going to list it down here. Hydrogen has a valence electron each, so we put it as 1, but because there's 5 of them, that's 5 electrons. Nitrogen also has 5 electrons, so with that in total, we just add this up, 4 plus 5 plus 5. We have a total of 14 valence electrons we have to account for. Now usually the way you want to do this is that because carbon and nitrogen are the one with the most valence electrons, that's the one you want to center in the middle here. So you kind of just draw like, well actually let's not add the electrons just yet. We draw the carbon and nitrogen next to each other. And now, as you remember, 2 electrons, so drawn like that, this is a single bond. Okay? So, with that information, we just go ahead and start filling in the carbon and the nitrogen. So, this is what we have so far, a single bond between carbon and nitrogen. Now here, because hydrogen is 5, we can kind of just offshoot and try to throw in as many hydrogens as possible. Because I'm very familiar with this, I have a certain way of doing it. But first, let's do it in a way to where we didn't assume. So let's say this was one bond here, right? This is counted as 1 of carbon's 4 electrons and 1 of nitrogen's 5 electrons. So nitrogen still needs 4 more and carbon still needs 3 more. So let's just fill it in here. 1, 2, 3. So that's theoretically carbon right now, and nitrogen would be 1, 2, 3, 4. So carbon and nitrogen are now quote unquote done in what they can contribute. Now we start throwing in the hydrogens. I just like throwing it in every corner that's free, aka has only 1 valence electron or even none, depending on how complex question be. Usually it needs at least 1 though for the bond to actually form. So hydrogen, we just throw it in there for every part that has 1. So, and we know hydrogen each comes with 1 valence electron, so we kind of just add that in there. And funny enough, actually, we actually get the 5 hydrogens, 1, 2, 3, 4, 5. And if we count the valence electrons, it should actually equal 14. So let's see. 2, 4, 6, 8, 10, 12, 14. Perfect. And now as a last step, we try to see if this is actually their preferred state. So what we do here is that carbon, as we stated, it originally starts with 4. And let's see, based on the formula that I'm going to write down, if it still has that net charge of 0. So carbon, okay, 4 is its preferred value. Subtracting all of its non-paired electrons, which is 0, plus its paired electrons, so it has 8 of those electrons, but it's divided by 2 since it's paired. So that's 4. Oops, sorry. So that's 4 minus this, and that gives us 0. And now for nitrogen, we do the same thing. Nitrogen prefers 5 minus, notice that it has 1 lone pair, so nothing attached to it. So we can put 2 here, plus, but it has still 6 of them that's attached. 6 over 2 also equals 0, because this is a 4 here, this is a 3 here. And now for hydrogen, just to double check, it's 1 minus 0 plus 2 over 2, which is a 1, and that's also a 0. So that fulfills all our requirements. If we now go back to the question, we'll see here, this is exactly what they have. So with that, this question is indeed correct, and we can now move on to the next question. So question 2. Hopefully you can read that. This question is asking us to name each compound as a phenol. Okay, so that seems quite wordy, but we'll break it down to understand what exactly a phenol is. Okay, so phenol is going to have a group, an R group, like a carboxylic group, and it's attached to an OH. That is the basis of a phenol. It's an alcohol. Well, actually, just to make sure, because I noticed that it's actually phenol, so PHEN, that actually stands for phenylalanine. That's how you spell it. But that's pretty much what it's trying to say is that it has a benzene ring. So we can't forget that. So it's actually not this. It's going to be a benzene ring and an OH. And somewhere in this, so this is a phenol right here, as basic as it can get. But somewhere in there you can add some groups in there, and it changes the name of it, but it still keeps phenol at the end. Okay, and that's a key part, because now we know that, at least that information. So let's just write at the top, because we know it's going to end with phenol for 2 of them. I'm going to put a phenol here and a phenol here, give it some space. All right, and now we're going to draw these compounds. Now I do draw them slightly different. The circle just implies resonance, because as you notice, those bonds that you see there, okay, they're always switching. This one will move over here, this one will move over there, this one will move over here, so it kind of forms a circle, hence why I draw it like that. Okay, but some softwares may not be able to show it like that. That's why they have it like that as well. Well, with the bonds instead of just the ring. But here we'll draw our first one. So we have the OH here, and our second one okay, not the most flattering pics, but hopefully it can at least show what I'm trying to do here. There we go. Let's move this a little more down. All right, so now where this carbon, the methyl group, is attached to the bottom, CH3, that's methyl because it only has 1 ring, which will actually help us answer that question later. And now there's 2 CH3s attached to each wing here. Now with phenols, the cool thing is that where the OH is attached actually tells you where your starting carbon is, because it wants to give the most priority to where the phenol is. Because of that, we can actually label this as 1. Now it doesn't really matter which direction you go, as long as you start with 1 at the carbon attached to the OH, okay? That's the only way this works in terms of the name, in terms of proper naming. So with this, I'm going to go this way. So 1, 2, 3, 4, 5, 6. Same thing for the other one. 1, 2, 3, 4, 5, 6. All right, so we've done that. Now, the way the naming works for this is that you want to be able to say the subgroup, the name of it, and where it's located, starting with the location. So here, the methyl group is on the 4. So this is 4 dash methyl phenol. That is a name for this compound here, because that tells you that there's a methyl group, because there's only one carbon, methyl 1, ethyl 2, etc. And it's on the 4th one. So that's it for this question. Now here's a little bit trickier in the second one, because there's actually 2 phenyl groups on the 2 and the 6. So with this, you still want to make sure you put where it's located. So you put 2, 6, okay, and the space. Now, funny enough, there's also a way to account for when you have multiple of the same thing. Di for 2, tri for 3, etc. So in this case, they're just putting methyl. You put 2,6 dimethyl phenol, and that is the name of this compound here. Now hopefully you're able to follow along, and more so I was able to do this correctly, so that way you just follow the steps for this. In terms of naming these compounds, it's important to recognize what counts as a phenol at first, because looking at this, you might try to figure out, okay, how do I account for the OH group and the methyl group? When they say it's a phenol, and also usually how it goes, because there's a stronger group, it takes priority, which is why that's how it's going to end, instead of it being some methane ending. And then now that you know what your basis is, like your picture of what a phenol is, as we refer to here, you can kind of then go to figure out what's attached to that phenol and then name it accordingly. So for this, I am impressed, because 2-ethylphenol is not correct, because that would actually, so if we had our phenol group, okay, with the OH, depending on where you started, let's say the 2 was here, that will be 2-ethylphenol, okay? And if it was, for the second one, 2,4,6 trichlorophenol, there's a possibility here that they may be seeing different compounds than we see, but for your reference, so if you want to take a screenshot of this or anything, so that way you know for future reference, I'll also write down the names right under it so you can keep track. But for this question here, if it was 2,4,6, as we said, this is the 2,4,6, and chloro means chlorine only, so that's what that would look like. So this is 2-ethylphenol and 2,4,6 trichlorophenol. Okay, so I'm just gonna say that this is not correct. If we had, maybe there was a second part of it, they're definitely on the right track, but this is what those would look like. So feel free, take a snippet, review your nomenclature. Very important when it comes to things like these, because these questions do pop up on occasion. And with that, let's move on to question 3, the next question, okay? So, question 3. Ooh, now this one is fun. So, first, you want to classify the following pair of compounds, okay? Pounds as same and enantiomers diastereomes. Okay, so just to make sure, so enantiomers, I want to make sure I'm explaining this right because it can get quite complicated. So same, let's just start there actually. Same means that the compounds are the same thing. So it means that it's not like a mirror image, it's literally the same compound, as in they have the same R and S in terms of like rotation, and everything else is just, you know, from a different angle. That's why it's very important to do the next steps we're about to do to figure out which one it is. Enantiomers, on the other hand, they're like the literal mirror reflection. So it's like if this one was rotating clockwise in terms of this chirality, that one will be rotating counterclockwise, and it follows suit, as in every single part of it is an opposite reflection of each other. Okay? And diastereomers, hard words to pronounce, those ones are not the exact mirror reflection. It's like one or multiple parts are interchanged. So if this one was like a clockwise rotation, this would be counterclockwise. But overall, there's still that missing, like that piece that's similar, so it doesn't form that mirror reflection. In fact, actually, it would probably be easier to draw it. So same, if this was like, let's say we had a simple combo like this, where it was like R, R, this one would be R, R, okay? Or even like S, S. Because realistically speaking, it's just kind of like looking at a different side. But I would go, if you wanted it to be the same, I prefer if it was just like literally the same thing. Enantiomers, okay, mirror reflection. So actually, same has to be literally the same. Do not, because in this case, that's what an enantiomer is. It'll be like SR. This is a mirror reflection. So, scratch what I said earlier, same has to be exactly the same. You'll notice that depending on how you draw it, specifically if you follow the right way, it should end up showing up as the same thing if they are the same. This is what enantiomers look like, and diastereomes look like this. Let's say this was RS, this would be like SS. See, two of the same, but one part is flipped. And then constitutional isomers is when they have the same name but built completely different. Like let's say one was like a ring and the other one was like these two technically, if I drew no benzene ring, just an actual 6-ring hydrocarbon, and then this 1 2 3 4 5 6, they're really the same thing, because if you actually count 8 4 5 6, oh no, they need a double bond in here somewhere. But the point being is like this would be like C6H12, and this one 1 2 3 4 5 6 7 8 9 10 11 12. Yep, this is also C6H12. These two are constitutional isomers. They have the same, they're constituted of the same thing, but they're literally different. And last but not least, not isomeric, just different compounds. So but we're focusing on those 5, okay? And now we're going to see 1 and 2. So now with these questions, we have to actually kind of do the second part before the first, because only by finding out its rotation, its chirality, can you say whether it's actually one of those 5, okay? So with this, the way you draw this, you have to be very, very careful about this, because it did take me a bit of time, but when you look at this picture, for example, okay, so you have, let's actually draw the whole thing here, because that's a little bit easier to explain. ClH, this is CH3, that's why you don't mention it. ClH, okay, so this is what we have for the first one. So the I'm going to use a highlighter for this. The bend here shows the parts that are kind of sticking into the page, if that makes sense. Okay, and the top bend shows the parts sticking out of the page. So we have parts sticking into the page, sticking out of the page, and you want to draw specifically to where you're accounting for things sticking into the page and out of the page. Me personally, I drew it if I was looking at it, if I had an eye view. Let me just change this over. I drew this part looking at it like that. Okay, so if I'm looking from top to bottom, this is what I see, okay, like that. I see the chlorine at the bottom, sticking into the page. I see a carbon group, the CH3, sticking out to the left, and I see hydrogen as it's shown there. Because remember, the dashed lines, that just means that it's going away from you. So technically, when you're looking down at it, the hydrogen's on the right. It is very weird, something you have to get used to in terms of this question specifically. Now that leaves that this rest of the thing, the R group, is at the top. That is what I see here. Now, with that though, okay, you have to also keep, in a sense, that same viewpoint, because now I'm looking at this one from here, okay, to get this picture. And in this area, I get, okay, that the carbon group CH3 is at the top, okay, the R group, like the rest of the chain that expands, to the bottom, chlorines to the left, okay, and hydrogens to the right. So that's what I'm seeing. But these two parts aren't enough yet for you to determine which way it's going to rotate. So you notice that the hydrogens for both of them are on the, well, in this case, the right. You want it to be at specifically the top or the bottom, but you want to make sure you do the same change for each one. If you're going to move the hydrogen to the bottom, because in a sense, you don't want the hydrogen to be on the pieces sticking out. And so you have to, in a sense, flip its position with something else. But when you do that, whatever direction you get, you have to inverse it, so that way you get the actual chirality, okay? So let's go step by step. I'm going to flip the hydrogen with the chlorine in this case, and the hydrogen with the R in that case, okay? So I get H is now here, chlorine is here, R, CH3, okay, and I get here Cl, R, H, CH3. Now remember, okay, this is the opposite. But now that hydrogen is, in a sense, out of the way, pointing in to the page, it's like we don't have to count anymore. We do our rotations based on the strongest group, and we move from there. Chlorine is the strongest group, and then followed by the bigger length, so the R, because that's where the rest of the things attach, and then the CH3 comes last. So in this case, if we were to trace, I guess, a circle, because we ignore the last one, we ignore hydrogen. We always ignore the fourth one. In this case, hydrogen is the weakest one, so we ignore that one. That's why I flipped it over. So it goes chlorine, R, CH3. So we're getting this rotation here, and that is a counterclockwise rotation. So that's an S, okay? But remember, this is in the opposite section. And now here we have chlorine, R, CH3, also going in the counterclockwise position. So that's also an S. So remember, because this is the opposite, our final result is that these two are going to be R's. That is what it is. So that means for this segment, that's an R. For this segment, it's an R. So they're both turning right. So that's the first part. See, this is quite a question. All right, so now the second one, Okay, because now we're on to the second part of this. We have that. And the reason why these questions can be difficult is because you really can't tell what you're dealing with until you write it out. From just a viewpoint, unfortunately, this information is hard to mean much, which is why you have to make sure that you take your steps one at a time. So now let's do the same thing here, okay? Bird's eye view, we're looking down, okay? So what we have is, imagine if I was, this is the nose here. That's a good thing to add because you want to make sure that you see, I want to make sure that you see what I'm seeing, okay? And then this person's head here, okay? His nose is actually going to be, just to make sure this our boy is like that, okay? So it's kind of like someone walked around pretty much and looked at it. Very weird concept, but that's how I understand it. It's just important that we just go through steps of how we're supposed to look at it. You want to make sure everything's, I guess, as similarly done as possible. That way you can actually notice the changes within each one. So here, when you look at it this way, the R is also at the top. We have the CH3 group here, the H here, and the CL at the bottom. And then for the second part, we have CL at the top, H, CH3, and the bottom is the R, okay? So same thing here. We want to make sure that the H, preferably at the bottom, just keep things constant. So we flip it over there, and we flip it over there, okay? And now what we get is, as a new thing, so this is now the opposite section again. You got the R, CH3, CL, H. And now here we have CL, CH3, R, H. And now let's see what we get when we track the rotation. So start with chlorine, move over to the R, then CH3. So this one is an R, okay? So remember, it's going to be the opposite of that. And here, start with the chlorine, move to the R. So this one is actually going counterclockwise as an S. So with that, you just flip it over. So now we get SR as the second one. Whew. So luckily for us, we've actually gone through the hard part. So now we can kind of just draw that next to each other. So we have R, R, and SR. Now this is not a mirror image. So this, and we know it's the same compound. Well, not same compound, but same constitutional structure, as it has the same things. And we also know that all that's different is literally one piece of it. So it's not a mirror image. So this will actually be a diastereomer, if I said that right. So just in case they weren't sure what I said when I pronounced it, that's what this is here, okay? So now we have that part, and now they're asking for the naming of it, okay? So the way I do this is I kind of just went through process of elimination. So we needed an RR and an SR, okay? So the only one that has the RR is the second choice. Now you notice that the pairing thing is RS on this one. Now these are very important for these type of questions because there's only two chiral points, as I said, and literally like they're the same thing. You don't know which one is going to be the primary carbon and the first carbon and the second carbon because of the fact that you could have started anywhere. I could have made this so like what here, because it says RS, we can say that they made this 1 and this 2, hence how they got the RS. But for me, when I was doing it, as you notice, I start from the top. I made this 1 and I made this 2. Hence how I got the SR. So with that, just be careful because you may still have the right answer. It's just important to account for the fact that they may have started from the other side. Just go over it, see where you'd like to attach your first carbon, and then go from there. So this question exactly would be, answer is B in this case. I'd love to write out the whole thing, so I'm going to pause it here for you to write down just in case you need this in this example. So compound 1 is 2R, 3R, 2,3 dichlorobutane, okay, which makes sense because there's a 4 CH3s, 4 carbons, and then 2 chlorines. That's it. And compound 2 is 2R, 3S, 2,3 dichlorobutane, also that. So diastereomer, that's what they are. Now let's see if we did it correctly. Oh, no answer. Okay, so we got our work cut out for us. So we can only hope that I did this right. So I'm going to leave that here just for you to quickly take down any notes that you want to. A lot of steps. If you definitely need more explanation on how to do the specifically the chirality, I definitely click on the link in the description below because we have wonderful tutors here and we can definitely further explain how we even get to the point of assigning whether it's R or S. Okay? All right. Now let's move on to question 4. Okay. Okay. So this question is asking us to determine the hybridization and geometry around indicated carbon atoms. So what does it mean by hybridization? Okay, what does, when I write down SP and SP2 and SP3, what does that mean? It actually simply means the amount of carbons, it just means the, trying to word this as correctly as possible. It's how many carbons, or how many functional groups the carbon has attached to it. I guess that's like the best way for me to break it down. So SP would only have 2. So if you remember the whole like 1S, 2S, 1P, 2P. So in terms of like that, but the way I remember is simply the S always, as in you're always going to have a carbon attached to something. Like this is like the most extreme case, but carbon always needs to be attached to one thing, and then the P is the second thing that's attached to it. So for in the case of SP, it'll be a carbon that's attached to 2 things. We don't know how, but you just know it's 2. SP2, it's a carbon that's attached to 3 things. Once again, we don't know how, we just know it's attached to 3 things. We don't know what type of bonds these are. Okay? And SP3, you guessed it, carbon attached to 4 things. We can assume that they're single bonds because of the fact that that's all carbon can take. But that is what the hybridization is talking about. Now, geometry, okay, we're going to write the correlating part. When a carbon is attached to 2 things, those 2 things want to be as far from each other as possible, making this linear because it's going to be a line, as in one is going to be on one end and that's going to be on the opposite end. Now, when it's SP2, so 3 things, those things want to also be as far from each other. Okay, so that one's going to be trigonal, planar. Okay, and now with that, the key part about this is that the reason why we put trigonal and planar is because if you notice, actually just in terms of geometry, it's pretty cool. When it's like that, right, 120 degrees from each other, okay, as it's a 360, that's actually the farthest points it can be from each other. in that specific case. The reason why I'm saying that in that specific case is because when you go to, the next one, tetrahedral. Let me just rewrite that. No one can read that. Tetrahedral. Okay, this is actually quite different. So this one is, it kind of looks like that. Okay, the exact angles are like 109.5 or something. And you're probably thinking, would it make sense to just have like a 90 degrees? Well, actually, because remember, which is why trigonal planar is even cooler, because this is, remember, it's a three-dimensional plane, okay? And that 109.5, they kind of, one goes a little bit into the page, one goes out of the page, and that shape kind of forms a little pyramid, okay? And that's actually the farthest all those four can be from each other. But in trigonal planar, it still prefers to be flat, because coincidentally, that 120 degrees, no matter what angle we try to put it, that's actually the farthest they can be from each other, and it still remains flat, hence why it has the planar to its name. Okay, so tetrahedral, definitely one of the weirder ones, but that is in summary what hybridization is. And now it's asking you for each of these certain parts. So A has CH3 attached to that functional group, so it kind of looks like this. So we put R, because R notifies the rest of the chain that I don't want to draw, and the rest of it is H's. Okay, and as we discussed, that would be sp3, making it tetrahedral. Why? Because it's attached to four things. Now B is a CH attached to two functional groups on each side, so kind of looks like, so we have the H, and this would be the first functional group, this would be the other functional group. We just put like R1, doesn't matter which one it is, point being as long as we can show it. And specifically at B, at R1, it has a double bond. So the double bond doesn't change much because it still follows rules that it's attached to three things. Remember how we discussed we don't know what type of bonds it is? Hence how this one is actually an sp2 and trigonal planar. Okay, and now for the last one, that one's C. You might guess it. It's going to be C attached to a CH3, and this is the one in question here. So let me just circle it. Okay, attached to a functional group, but that functional group actually has a triple bond with it. So, like we said, we don't know what's attached to a bond. We just know it's attached to two different things, making this one SP, and this is a linear. So that's what we have for the geometry and hybridization of each indicated carbon. Okay, so let's see. Oh, well then. So hopefully we did this correctly. Just as a quick review, as I said, the hybridization can be broken down simply to how many things it has attached to it. It does go into like, the shells and like, the P, SP1, SP2, like when you're doing all that, but we really don't have to do that. We kind of just can skip to, okay, how many things is it bonded to? And then we go with that. Things do go past, SP3. I think it's like SP3D. That's when you have those really weird, like the exception, like sulfur, for example, can attach to six things. So there are some exceptions to this, but when speaking about carbons, sp3 is as far as it's going to go. Okay, so now let's go into question, I believe it's 5 now that we're on. Yes. Okay, so we want to arrange the following in the order of increasing boiling points. So this person actually knows the correct order, but don't really understand why they're in this order. So let's just write it out. So arrange in order of boiling point. Okay, we have magnesium chloride, helium, okay, water, methyl chloride. Let me just think about that actually. Chloromethane is probably what that is. Yeah, that makes more sense to me. Argon and carbon dioxide. So that's a lot of them. So the way this one's going to break down is that we want to first separate it based on the type of I guess molecule or atom. So right off the bat, when dealing with atoms, helium and argon, the smaller it is, the lower the boiling point. So helium and atoms literally lose. If you're an atom by yourself, most cases 9 out of 10, you're gonna have a lower boiling point than everyone else. Okay, and they got that correct. So they're actually confused about the later parts, but I'll show you how we can determine it. So we know it goes helium, argon. We have our first part. Okay, so that's how you take care of that. Now you want to do the next parts based on, if you remember, you know, your London dispersion forces and your covalent bonds and then your hydrogen bonds. That's what you want to focus on next. So, and ionic bonds, that's the last one before I forget. So with that, ionic bonds being the strongest, okay, an ionic bond, remember, is with a metal and a non-metal. Glancing over these, the only metal and non-metal is magnesium chloride. This right here is an ionic bond, meaning this is going to be the highest boiling point. So that one's going to be at the end, we add later. And that just helps us hone down to these three. Now, as I said, ionic is top, okay? So I'm going to write it actually down here. Ionic, which is the bond. Then it's going to be, well, dipole, dipole. But actually, you know, before I put dipole, because I know there's pretty strong dipoles, but hydrogen bond is like up there as well. Those ones beat out most, if not all, dipoles. Because dipoles, they still form, like, there's still a distribution of electrons just where they prefer to be, which does increase the boiling point, but hydrogen bond is like really polarized. And then after dipole, we have just covalent bonds, because it's not really much in terms of difference. So dipole, you know, do technically count as covalent bonds, but covalent bonds, in this case, I'm implying that they don't really, the net charge doesn't really prefer to be anywhere, as in it's pretty neutral throughout. It doesn't really have a polarity. And then that is pretty much how we break it down there. Okay, so with that, we're going to see in terms of these how it break down. So as I mentioned, hydrogen bond's the next one, so H2O follows suit, okay, because that's how it's broken down. So boiling points will increase this way. So we have the highest and the second highest. So now, as a student was asking here, how do you know between CO2 and CH3Cl? In this case, just draw it out and you will see from there. So CO2 looks like this: O, C, O. Okay. That one, as mentioned, this will technically count as an SP, hybridization, because only bond two things, and it's linear. Okay. Look at that. The pool is completely even. So this one will really be more of a covalent bond. It has no where it wants to be pulled to, hence how we get that. And when we draw CH3Cl, that one, Cl, Cl is quite high on the electronegativity scale. So this here will be kind of like G minus, attracting most of that charge in this corner. So everything will kind of be pulled this way towards a Cl. This is more of a dipole than this one, and because of that, because of literally that pull, that makes this have a higher boiling point than CO2. So if we were to finish this up, CO2 would actually be next, okay? Then CH3Cl, then H2O, then our ionic MgCl2, okay? And that's why, because CO2 doesn't have a pull, like it doesn't have any polarity. CH3Cl on the other hand does, okay? And here they do talk about it as well, actually. It's a non-polar molecule, so exactly, it's just a covalent bond. CH3Cl is a polar molecule, has that dipole, hence why it's stronger. And then H2O, as you discussed, that's a hydrogen bond specific case, that's why it's so strong. And then MgCl2 tops them all because it's an ionic compound. So exactly, this is correct. And now let's move to question 6. All right. Okay. So this was just asking, at a given temperature, the reaction A to B, and they have these arrows because it's reversible, has a constant first order, so it's in direction of the first order, which just means that if you're going to write down the formula, which we'll do later, it's going to be to the power of 1, okay? But the point being is that this first order reaction is, so the K forward is 2.9. Actually, I don't want to scroll over because that makes things annoying. Just gonna write under it. Equals 2.90 times 10 to the negative 2. And now, and that's just the units, seconds to the negative 1. That's what the units specifically for first order reaction. Now the reverse reaction is also first order, so the reverse reaction of this, okay, is going to now be, so K reverse is equal to 5.00 times 10 to the negative 2, same units, okay? Now, a forward reaction, okay? This is where it gets really strange, because you want the equilibrium constant, all right? So K forward, okay, is equal to products over reactants, all right? So that's what we have there, products of reactants. And then KR, the reverse, is equal to, you know, reactants over products. Okay? And we want a value of the equilibrium constant. So aka when KF, okay, when the rate of one side, well actually, you can have just K, and we want it when, you know, I guess KF, the forward and reverse reaction are happening, I guess, at the same time to form that equilibrium. So what you want to do then is you want to actually put KF over KR for that, for the reaction A to B. You want the forward over the reverse reaction, okay? And as we discussed, the forward reaction is that number here, the 2.90, and the reverse reaction is 5.00. Since they're both 10 to the negative 2, we don't really need that. But pretty much our K equilibrium constant from A to B is equal to just 0.580. That's what we get. And now we kind of just follow the same thing for now for the reversal, because now it's just going to be KR over KF, and it's just going to be 5.00 over 2.90. So that means this equilibrium constant, KBA, is equal to 1.72. Now, with these type of questions, the thing you have to remember is that when they're giving you the rate constants, that's what you want to be able to use to find the equilibrium constant. So they're giving you both directions, and what you have to do is pretty much just manipulate the equation. When they're trying to find the equilibrium constant for A to B, aka the forward one, you want to put the forward rate at the top and the reverse rate in the denominator. When they now go backwards, B to A, you want to make sure that you put the reverse rate in the numerator and the forward rate in the denominator. Okay, so that is how you would solve this question. And you notice it doesn't really have any units because of the fact that it's just two rate constants divided by each other. So let's see what we get here. So K equilibrium for the first one is 0.580, and then for the second one is 1.72. Perfect. Now we just kind of kept our significant additions, hence why I went this far. I did do the calculations beforehand, but exactly, see, here's what they did. Exactly, they have that the K forward. So just as a breakdown, just to make sure I'm doing this right. Okay, so this is actually a different part, so we can actually put this to the side. That's where you want to find concentrations. But in terms of when you have the so that's a different K, which is a little bit frustrating. So in fact, for your sake, I'm going to erase that, because the equation you're actually talking about is a rate of, the equation is equal to, you use the constant that they gave you, the K forward, and then A, okay, to the power of 1, because it's, remember, it's first order, and that's the forward one, okay, and the rate reverse is KR B, okay, 1. And that's now how we go to this part. Okay, so what we're really doing is the full, I guess, equilibrium constant in this case. Now we're back to actually look for concentrations. Well, not really, but more so like the constant. A lot of different K's, you have to just watch out for that. It's pretty much going to be, depending on what we're solving for, the RF over RR. Okay, and then that's how we then break it down to this one, and then we solve the equation. So that is what we do for that question. If you have any more questions, just exactly, we always have more tutors, and we always want to help. So this is correct. Okay, and now question 7. Which of the following molecules, so which, well, ions have a positive charge? So we have hydrogen carbonate. So hydrogen carbonate looks like this, HCO3. Remember, carbonate is just one thing you have to remember. Carbonite would be CO2. Well, in very different scenarios, but point being is that carbonate is HCO3, and it just has hydrogen attached to it. B, ammonium, that is just NH4, C, sulfate, is just SO4. D, nitrate, is just NO3. And E, hydroxide, is OH. Now, these ones, I'm just kind of naming them because I'm very familiar with the chart, but exactly, it should tell you what sulfate, sulfite, all those things. Like, you just have to remember them because you have to remember how many oxygens they are, because you never want that to trip you over. You don't want to be adding too little or too many oxygens, and it depends on the name, which should be shown on the cheat sheet, and be able to be able to name those. So with that though, now along with the sheet, it also tells you, funny enough, what type of charge it has, like whether it's plus or minus. But in this case, it's actually a way to figure it out. So HCl3, okay, if you just drew it out, it kind of looks like, I'm just kind of making this up as I go, because it's carbon, H, O, 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 okay. And in fact, actually, yeah, it just helps me visualize. But the point is here is that carbon, according to the periodic table, if you remember from before, 4 electrons. O3, that's 6 times 3, that's 18. And hydrogen is just one of them. So 1 plus 4 plus 18. Okay, so in total, that would be 23 electrons it has to account for. Okay, so if we did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Interesting. Let's make sure. Oh, I see why. I went a little overboard. So remember that each bond counts as 2, okay? And we only want to fill in as much as we can. So in this case, we have 8 right now, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And now we notice that won't work. For it to be complete, the best thing for carbon to do is that instead of doing that, forms one double bond here, because this CO3 looks actually quite complicated. So with that though, we notice that 23 isn't enough, so we need another electron for it to, in a sense, quote unquote, be full. And actually, there's a much easier way to do this. I don't know why I didn't think of this. Sorry about that. We just use numbers. So O likes to be -2, and hydrogen likes to be +1, and carbon likes to be +1. But in HCl3, the way it breaks down, so it's -2, so that'll be -6 in total. Carbon has to make up for that, but carbon can only go so much. Hydrogen is going to be the +1 here, so +1 -6. Carbon can only go up to +4 because it only has 4 valence electrons. So 1 plus 4, that's 5, -6. HCl3 is -1. Okay, that is how you solve that one. It's a little bit tricky because these numbers can seem a little bit arbitrary, but in terms of think of what they can offer and what they can take. Nitrogen, okay, that one can be +5 technically, okay, and hydrogen in this case, because nitrogen is very, very strange in this sense, it really likes giving away hydrogens or like quote unquote electrons. So hydrogen likes to, in this case, play the -1 team, so that's -4 here. So NH4 actually would be NH4 plus. These are some things you also have to memorize because they actually do tell you the charge right off the bat. Sodium can only give away 6. Remember, oxygen is -2, and there's 4 of them, so that's -8. So in this case, SO4 will be 2-. NO3, nitrogen can also just 5, oxygen minus 2, so it's minus 6. Okay, so NO3 is actually a minus, at least it should be, and OH minus 2. Okay, hydrogen is plus 1, so it'll be OH minus. So sorry about the earlier part, but the summary is that once you have this breakdown, by kind of working through your charges, then you can figure out which one it is. And you notice that the only one it would be is ammonium. We could have just skipped to the part where we said that, oh, it's ammonium because we know what the names are, but this kind of charge distribution helps you figure out which one is actually the positive charge for the polyatomic ion. Now let's see. So exactly, this is correct, but I don't really explain how. But exactly, that's why I just wanted to break down in terms of the numbering in this case. Okay. And now for our last question for today, we're going to solve question 8 here. Okay. So a sample of glucose. So question 8. Okay. A sample of glucose has, so C6H12O6 has 2 times 10 to the 22 atoms of just C, carbon. Okay. How many, actually just put A, B, and C here. How many atoms of H? How many molecules of glucose? How many moles? And what's a mass? So that's a lot of questions just from that little information. The good thing is that we can actually find all those answers. So right off the bat, okay, we have something that's dealing with atoms. So we need Avogadro's number, okay, and that's the amount of particles per mole. That is 6.022 times 10 to the 23rd atoms per mole. But that will come in later, okay? Because right now it's asking us how many atoms of hydrogen. In this case, we just use ratios. So 6 to 12, right? That means for every 1 atom of carbon, there has to be 2 atoms of hydrogen. So by using that ratio, actually, we can actually answer this right off the bat, that there's going to be double of that. So that's going to be 4.0 times 10 to 22 atoms of hydrogen. Okay, so that was relatively straightforward. Now with this, we can actually also say how many molecules of glucose, because remember we're still dealing with atoms, so for every 6 carbons there's 1 glucose. So now it's a 6:1 ratio for the glucose. Okay, so with that we just divide the 2 by 6. So it ends up being like 1/3, well, 0.333. And just remember that because it's 10 to the 22, when you go down one lower, it's going to be to the 21. But in summer, we do get, 3.33 times 10 to the 21 molecules of glucose. Okay? So that's what we get there, and the 3 is repeating. And now it's asking for how many moles. So remember, we have this Avogadro's number here, but that also applies to molecules, particles, etc. Okay, because you want to go from atoms to moles, so you have to divide these molecules by Avogadro's number to give you the moles. So we have 3.33, or repeating, times 10 to the 21 particles. let's just use that to make it easier. Okay, and we know for every 1 mole there's 6.022 times 10 to the 23rd particles. Okay, so when you put it like that, you see that your units cancel out, leaving you with the moles. So that's perfect. And the number we get here, because I did the calculation beforehand, was 5.5 times 10 to the negative 3 moles. And that is how many moles we have of glucose. Okay, and here, just to avoid confusion, so say molecules, I'm going to say particles. That way we know we don't say mole and mole and we get confused. So we have 4.0 times 10 to the 22 atoms, 3.3 repeated times 10 to the 21 particles, and 5.5 times 10 to the negative 3 moles. So what is the mass of this amount? So the way we find that out is relatively straightforward. We need the molar mass of glucose. So the molar mass of glucose, if you refer to your periodic table, you have to make sure you get times 10 to a negative 3 moles, alright, multiplied by, we know that it's going to be 180.156 grams per mole of glucose. So you see here, the moles indeed do cancel out, leaving you with just grams. So the answer here, so I did calculation beforehand, we have, funny enough, around 1.0 grams of glucose. Right, yeah, coincidence? Huh, who knows? And that right there should be our answers for each part. Let's see how they did. So yep, 1:2 ratio, so they do get the 4.0 times 10 to the 22 atoms of hydrogen. And now it's 1:6 ratio. They definitely got the 3.3 times 10 to the 21. Perfect. And now they got our 5.5. Interesting that they put 0.5 to. It's the same thing, they just didn't want to move decimal one more place, but that is what we got as well. And then the last part, they have a closer number, 0.9936. I just rounded up because I only had 2 significant digits, so that's why I put the 1.0 grams. But this is correct. So it shows that even with the smallest information, you can just get every part of the question. Just make sure you keep it along with your units so you don't get confused in any section, okay? So with that, let me just end it here. So once again, thank you for joining me this evening. My name is Fejiro. As I said, if you have any other questions, definitely don't hesitate to click on the link in the description below. And with that, have a very good night.